Good afternoon, everyone. My name is Steve Liu, and I'm a first-year student at the University of Southern California. Today, I want to share with you a computational journey about how I went from receiving a challenge from Stephen Wolfram to discovering the hidden patterns in one of mathematics' most famous unsolved problems. Well, a problem related to this problem. So the title of my talk is The Computational Exploration of Generalized Collatz Using Wolfram Technologies, and this is a story about curiosity, computation, and unexpected discoveries. So this is the outline of this presentation. We're going to go over some backgrounds about the Collatz. We're going to introduce the specific problem we're going to explore. I'm going to show some computational ways of exploration, and then we're going to go through some visualizations, and then we're going to have a conclusion, and then into the Q&A section. So this project exists as a WSS project proposed by Stephen Wolfram. WSS is essentially Wolfram Summer School. It's a short period where we go around and then have a project and we explore a lot of stuff. So for me, I specifically choose the Collatz conjecture or the generalized Collatz conjecture because I think it's very interesting. And the fact that not a lot of research has gone into this field means that I can make a lot of this interesting discoveries on my own. And I kind of want to just explore something that hasn't been explored before. To start, we're going to start with the Collatz conjecture. Now, it's actually very simple. So basically, you start with any positive integer, and if the number is even, you divide it by 2. And if the number is odd, you multiply it by 3 and add 1. It's very simple. So let's take 11, for example. You can see here that we have 11, it becomes 34, 17, 52, 26. It alternates increase and decrease. Eventually, it converges to 4, 2, and 1. And here is where the Collatz conjecture lies. Basically, the conjecture states that almost all numbers converges to this cycle of 1, 4, and 2. After 1, you basically jump back to 4 and then goes to 2 and 2, 1. So this is the cycle. So it basically converges to this. And it is also important to note that although Collatz remain unsolved and true but no proof, there are many statistical arguments about this conjecture. And it's not hard to see why. Basically, for the operation of 3n plus 1, it basically increases the number significantly, but that's also counterbalanced by divided by 2. So on a statistical level, basically it's a convergent sequence. Basically, it's proven that it's convergent. And this is related to our exploration in the fact that we're looking at a more general form of Collatz where it could have a lot more different conditions. And this is the generalization I decided to go with. It's a pretty simple one. Basically, if you have, if your number is a multiple of a given d, you basically divide it by it. And if it's not, you do mn minus r, and then you divide by d again. Basically, this is so that we can simplify the steps a bit, that after mn minus r, it should be able to be divisible by d again. So after that step, we basically just divide by d anyways. So by doing so, we just simplify it and then basically makes the computation a bit simpler. Keep in mind that for higher d, there will be more terms on this. So for example, this is for a mod d equals to 2. If you have d equals to 3, we're going to have a third term here, mn minus r over d, for a different remainder. And putting it all together, here's a sample, pretty simple function for this generalized Collatz. You basically input a set of integers, one for the coefficients and one for the constant. And it's very simple. And here's the question we're actually going to explore. We're trying to find what if we can find a function that's perfectly balanced, meaning no bias towards convergence or divergence. Well, what does that mean? Well, basically, you can see from actual Collatz that it converges. It goes down to a very small specific loop. Now, that's convergence. How about divergence? Basically, it goes to infinity. What we're finding is a function that kind of stays on its own. It kind of just doesn't go to any value that's like infinity, or it doesn't go down to a certain loop, a specific loop. So that's really what we're exploring. And as you can see on at the conclusion part, we're going to have some functions that are pretty close to this definition. So to start, I started by exploring a system proposed by Stephen Wolfram himself in one of his writing. And the title is, After 100 Years, Can We Finally Crack Post-Problem of Tag? That's a different problem, but he uses the system to illustrate something in this computational essay. So basically, we have the system 4n plus 2 and 7n plus 1. And basically, this is a very similar sequence. It's a similar Collatz sequence from the original one before, but this time we have three terms. And so as a result, we have three different ways of reaching any given term. And so let's put it in 11. And here's the sample. You can see that this is kind of like what it looks like for the same initial value. It's kind of like different, but yeah, it's basically alternated between increase and decrease as well. And so to actually like study the behavior of the function across a wide variety of the initial conditions, I decided to test a random sample of a wide range of values and then take the logarithmic average of a given percentile of the range of initial values. This meant that we're basically segmenting the initial values by its like value into different percentiles, and that would allow us to kind of see like what's the behavior for each initial value in a given percentile. And this is the resulting graph. As you can see, the 90 percentile, the top ones, actually seemingly diverges. It doesn't really converge to any values. You can see for the 80 percentile, it actually it does try to like diverge, but then eventually converges around 1500 steps. And for the other ones, it kind of has that similar pattern as well. Now that is very interesting. It kind of just shows that as the values get bigger and bigger, it kind of has like more divergent values in it. And so the first question I actually have after receiving this graph is that, does this 90 percentile exhibit similar behaviors as this one? Like, does it actually eventually converge? Now, well, I ran it for more steps, obviously, and I only look at the 0.85 and 90 percentile of this specific condition. And this is the resulting graph for that second computation. So as you can see the label over here, I only explored from 0.85 to 0.99, and I plotted in a more 1 per 1 percentile because I can see more kind of like fine grain of how the function behaves. And you can see for the lower ones, it does actually eventually converge well after about 3,000 steps. But for the top ones, it simply diverges into infinity. And especially with this one, it has a really high slope, and that just keeps on going. And it's very interesting, right? It seems that for the higher initial values, there's higher chance for divergence for the initial values. So basically, they have a higher chance of divergence. And why is that? For values, and then we also explore the values below 1,000. Basically, for values below 1,000, only 469, 487, 626, and 650 diverges. And 469 is a given divergent value by Stephen Wolfram in his writing. And so you start to wonder, what's the relationship between all these numbers, 469, 487, 626, and 650, right? And it's actually pretty simple. They're basically numbers on the divergent sequence. If you put in 469 into the Collatz function, we basically get 469, 626, 487, and 650 on the sequence itself. So basically, they're all a part of the same sequence. And here's another interesting thing. 469 is actually the known smallest value that causes this divergence. You can see all the other values here are all inside this 469 sequence. And just a quick note, for the implementation in Mathematica, we use it as a nest list to kind of have a recursion onto the function itself. And I kind of started plotting in a different plot. This is basically showing the percentage of value that diverges, so that I can see that how many values as you get to higher and higher plots starts to diverge. And it's kind of surprising that about like 76%, which is a pretty huge majority of them, is actually divergent. And it's basically infinitely large numbers that's divergent because, as you note before, that sequence is divergent. So as it goes to infinity, the number just grows infinitely large. And so this causes that more numbers more large numbers will be more likely to be in the divergent sequence generated by 469. You can see there's kind of like a little trend, like kind of like linear trend in this part that kind of like goes from 48% slowly to 76%. And it seemingly does actually just increase all the way up to 76%. And here's another plot. Basically, this plot, I'm looking at values below 1,000 so that I can make sure that the behaviors here is actually just, it doesn't actually like have any values that kind of like diverges. And what you see here is you can see the four values that I mentioned that for sure diverges. But you can also see there's actually two values that doesn't quite diverge, but it kind of is close to diverge, but it eventually converges within quite a huge substantial steps. And you can see a lower tier here that converges in the faster steps, but and then eventually go down here to the majority where it converges really quickly within about like 10 or something steps. But you can start to see some patterns where it kind of just like clusters together. Like you can see these two are about like the same region. These also belong in the similar regions. Um, the middle ones and the especially the lower ones, they all belong to a distinctive region. Especially the lower one, you can see the lines forming. So it's kind of interesting to see that this is kind of behavior, and this is also why it kind of influences the plot we see before. This plot, basically how like in the lower part, it kind of seemingly diverges, but it converges. This is also influencing that as well. So there's actually one more thing. I kind of did mention it, but basically, since we're testing mod 3, there's 3 ways of reaching any given value. And our divergence sequence technically only illustrates one way of reaching each element. So basically, we're generating a forward sequence where each element is basically generated from a previous value. So theoretically, there should exist 2 more sequences from any given initial value that converges onto our original 469 sequence. So that means that we can generate this number on the sequence, let's say 487. Instead of using 469, we can use some other 2 values that also give us 487. And that means that anything that has any like sequence that contains any value inside the 469 sequence is divergent. So given this thing, you can generate an infinitely divergent space, a web of infinitely divergent space. And this is what I did. This is the result. This is the graph. You can see here that the red line illustrates the 469 sequence, the forward sequence. This is 469 over here, starting from here. Then we goes all the way to a pretty huge number. And the gray branches illustrate the sequences that diverges, the different possible ways of the initial values coming onto this divergent sequence, and thus that is divergent. You can see that the branches are kind of different for each one. You can see some of them are shorter, like here, and some of them are longer, right here. So what does that mean? Well, that means that basically the shorter ones basically means that there's less ways of reaching that given value. Because we're basically for this, we're exploring given a set steps for the branches. Because if you don't, the computation is going to be really expensive and it's not feasible to compute in a given time. So we basically limit the steps of the branches. And so if you see the branches being smaller, that means that there's some steps that failed and it doesn't actually allow us to converge to the value. So you can see here particularly, and then for 487, I think there's only like 1 branch coming off here. So that's very interesting. On a side note, this is the hero image for the community post I made, and basically this is a artistic rendering of this. It's using the same format and it's also made in Mathematica as well. Basically, I kind of just illustrate the steps by using a gradient. You can see the white over here. So the most recent step will be white, and then the least one will be gray. And you can kind of see how it diverges from this initial 469 sequences all the way outside. It's pretty cool. And to summarize, for this little section over here, although the bias prediction, the likelihood convergence or divergence state that this one actually has a slight divergence, the behavior of the higher initial values is very different from the lower ones. Basically, the higher the values you have, the more likely it will diverge. And it seems that the low bias values is only attained through the balance of divergent and convergent values. And it's pretty interesting, right? Basically, it's kind of like a fine-grained balance of these 2 conditions. So we're going to explore more. And there's 2 challenges for exploring more. Since we need a way to validate parameters, because if you don't, you're going to end up with a lot of invalid parameters. So we need to basically constrain this valid parameter space we're searching, so we don't actually end up with broken parameters. And we also want a way to determine the general statistical trend of any given parameters. We need a bias function, in short, because if we don't, we're going to end up with a lot of functions that doesn't really come close to being neutral. And having a bias function means that we can kind of estimate kind of how neutral is the function, and that would allow us to kind of like, after generating a few certain sequences, we can kind of just explore like more details, like what does it look like. So this is addressing the bias function. I basically just take the bias function from Stephen Wolfram's writing and using it, kind of like generalizing it to the more general terms. Basically, he uses basically the two coefficients over here, and then the bottom one is basically the mod number times the number of coefficients. And so we basically do that as well. Basically, we basically have all the multiply all the coefficients on the top divided by the value, and then that's going to be exponent of the length of the coefficients. And then we take the log base 2 of that, which is pretty simple. It's basically derived from the function over here, and it works decently well as an approximation for the bias. And we also have a value parameter set. Now, this is a bit more complicated, and for more details, you guys can read about it on my community post. But in essence, there's a term and a certain condition that has to be satisfied, specifically this one. And then that allows us to kind of validate whether each parameter of basically a coefficient and additive constant pair is going to be valid. And given those two functions, we can start estimating. And also on a side note, you may notice that our bias only takes in the coefficients, but from my experimentation, the additive constant of b, in the an plus b divided by d part, this one actually does kind of affect the behaviors of the function, as you will see later. But since it doesn't really affect it that much, it's within the given acceptable range. So we just kind of like just use the coefficient as the approximation. But more work could be put into making a better bias function. And let's share some of the notable discoveries. So this is a function I discovered in the mod 3 space. And basically what's striking about this one is that it seems that from the 0.5 percentile to the 0.8 percentile, you have this very orderly patterns that emerges. Basically, I hypothesize these are the loops, basically pretty huge loops, but they also like confirm pretty orderly. So that means that they kind of just like separate each other by like a certain value, but they all have the similar slopes and stuff like that. So it's pretty interesting. And you can see the top one, it kind of does actually converge as well, but it's less apparent. It seems that the balance of maybe convergent or divergent values may be a little bit different than the ones in the center. But overall, this is pretty interesting. Here's just a little like estimation of the bias, which is pretty close to 0. And that's pretty like neutral. And here's another one we found. Basically, here's a function that's pretty close to the neutrality that we defined. Basically, it doesn't go up or down. What happens here is that you can note these straight line regions. These are regions that any value converges to. And what happens is that you can see that from our bias prediction, it's giving a straight bias of 0, indicating it's a pretty like neutral function. And so taking a closer look of this, basically what happens is that for especially for values higher than like this really huge values, basically, the initial values are very likely to end up in a loop back to itself. So for example, for this one, we put in this number as initial value. And then you can see that the generated sequence basically includes itself in the loop. And for this one as well, it's pretty similar. There's also like some exceptions though. You can see that for this specific value, it converges all the way down to the 961 loop, which is significant, which is actually like a lot smaller than 123, which is kind of interesting, but it's not really surprising. You can see some of the bands going down here. You can see the red one down here, and then the two yellow ones are actually higher. So it's not surprising, but it's pretty interesting, and it's pretty neutral as well because it doesn't really go up or down by a lot. This is a similar function with the same coefficients. So that means that we'll have the same bias estimation value, but it's going to, I changed the constants, the additive constant, the D, the B values. So this is the parameters I have. And basically what happens here is that it kind of just different. You can see for the low ones, it kind of concentrates a bit more to like a region on its own, but the higher ones are a little bit more separated. And there's also some general trends across mod spaces. You can see that comparing the output of mod 5 and mod 4, you can see that for mod 5, the bias estimation returns at minimum 0.005. But for the even ones, mod 4, it returns a straight 0. And this is pretty interesting because the behavior we exhibit here is not going to be seen on odd mod values like mod 5. it's going to exhibit something similar to mod 3 behaviors, which is kind of interesting. You're not going to get that behavior on other ones. And some concluding remarks, Wolfram Technologies has been pretty instrumental in assisting this research. Basically, I was able to create a lot of graphs I wanted and then pretty quickly iterate on the mathematical computations. And some future explorations we can do here is that can we improve the properties of the balance variance? I kind of want to do that because basically it's kind of interesting to see how the properties have already behave with statistical arguments, but is that really concrete, like how they actually behaved? And do divergence transovers originate from the single sequences, right? We can see the 469 sequence, it does actually occur, but is there any other function that has a different way of divergent? And what happens in the higher mod spaces? Basically, due to computational limitations, I was only able to explore mod spaces up to mod 7. But for the higher ones, the behaviors might also be different. So that's something that I have to explore in the future due to the limited time. But yeah, it's pretty interesting. And thank you for listening to my presentation. Here's some of my contact info. If you guys want to read more about this research, you guys can look at the community post I made using this URL. I use this URL, and then stay tuned for Q&A.